Hello. Hello.
Yes, sir. You are audible, sir.
Sir, your screen is not visible, sir. Yeah, now it's visible, sir.
Hello, can you hear me? No? Hello?
Yes, sir. Yes, sir. Now I can hear you, sir.
Yes, sir.
Okay. Previously it was not audible last time.
Yes, sir. Now it's fine.
Okay. Can you see my slide now?
Yes, sir.
So I think we have gone through this just one last time. So welcome all of you to this live session of radio astronomy. We are on week 11 and almost coming towards the end. And we hope you are enjoying this course. We have tried to go slow in the second half of this particular course and try to revisit all the important concepts. I think we're trying to also give you relevant amount of practice problems that you can kind of reflect on what has been taught in through the first 8-9 weeks, and also how we are proceeding slowly after that. So I think that should be sufficient to prepare for your final examination. And we will also give you the, if you look at the 11th and the 12th week assignments, you will see that there are a lot of things have been revisited and discussed. So I think if you keep practicing those, I think and looking at all the assignments, that should be sufficient for you to, and take a look at the lecture slides, the videos which has been shared. It should be sufficient. There are a few more videos coming up this week and early next week, and you can go to them. It should be easy. The paper is not lengthy, nor it is quite descriptive. It's based on MCQs and numerical type questions. So I think what we will do mostly in the last few videos of this week and next week are mostly for a completeness purpose. Don't worry too much and concentrate more. If you're giving a final exam, concentrate more on the assignments which have been shared, and that should be sufficient. Okay, and we will. I think we've already shared a lot of materials, and we will share more. We'll make sure that they are available before by early next week. Okay, so when we come here next week, we will have a final, like take a stock of the situation, what else is there, and we will just close this. Okay, so but don't worry, there will be few lectures will be shared this week and next week. They are mostly for your understanding and completeness of this particular field called radio astronomy. If you're worried too much about the exams, I think if you follow the nature of the questions, types of the questions, and kind of things which have been shared in the assignments and asked in the assignments, those are more or less sufficient. Okay. If you have any questions, we will again answer it at the end of this particular session. Let us get started and finish a couple of things which would be we wanted to be completely clear about. So as we have seen, we've started with a single dish, and that has a particular diameter. We tried to replace that with a bunch of smaller diameter antennas and try to correlate the signal. We used the Earth's rotation for the Earth's rotation synthesis. This thing is more or less common, like what we have done in the Young's double slit experiment, if you have done it all. So it's more or less similar to that. We have seen there is a fringe between the two. If you have the two signals coming from the two antennas, there is we observe a fringe pattern like this, which is kind of similar to the Young's double slit experiment. We didn't refer to this before. We did not know, given the variety of students in this particular course, whether this will be quite another common experiment, or will it be another unknown experiment for this particular batch. So we didn't refer to this at all, but it's something like a Young's double slit experiment where you have the two slits over here, and they have a finite dimensions, slit width, and they are separated by a distance of b over here. Okay, and so this b is the distance between the two slits, and the b is also corresponding to the distance between the two antennas which we have discussed so far. And for any two antenna which are separated by a distance of b, which is called the baseline, will give rise to this fringe. And as the baseline with the length becomes larger and larger, the fringe frequency will become larger, and so that's one of the important aspects. So for one particular baseline, you have one particular fringe pattern. For different baseline pairs, antenna pairs, different baseline lengths have different patterns. So it's more or less exactly similar to what we have for this Young's double slit experiment, where you have a light wave coming in. There are two slits separated by a distance of b, and each of them have, say, a slit width of capital D, say, and this D is comparable to the diameter of the dishes, and B is comparable to the separation. What happens is if there is only one single slit, it only suffers diffraction, and if there are two slits, there is also interference pattern. So that's what kind of this is linked to. Not going further into that because I'm not exactly sure the diverse group we have for this particular course. That can be another different discussion for another particular course. So anyway, so we have also seen that in different pairs of antennas give rise to different kinds of fringes. If you add all of them up, then you finally get the UV distribution, which you have seen. And then if we Fourier transform that, you get a dirty image, which is kind of the image convolved with this particular PSF or the point spread function. And then if you do finally the calibration and the deconvolution, also known as clean, we finally get a clean image, or finally what we expect to see in the sky. Okay, that's pretty simple to look at. It's pretty it's a bit more complicated in actual practice. We have gone through this particular video where we have shown that for a single point source, we have a response which is kind of grows and becomes better and better as the number of antennas increases in this bottom left panel, and the UV coverage also becomes more and more regular and more filled. So one thing is very clear: to get a better image of the sky, you need more number of antennas. And this is a particular aspect. Please note that. So if you have more number of antennas, if more number of baselines, you have a better UV coverage. A better UV coverage gives you a better image. Please remember that. So that's one thing is very clear. So if you want to, depending on what kind of science you want to do with this particular interferometer, you will have different distribution of these dishes at different distances. Okay, we come to that in a bit. This we have already done. We have shown that the visibility so the visibility is a 2D Fourier transform in a particular assumption that it is only covering a very small part of the sky. So I, which is the image in the sky, is a Fourier transform of the visibility, which is in U and V coordinate system. And this in physical optics is also known as Van-Sitter-Zernike theorem. We have also discussed that the baseline, which is the distance between any two antennas and its components in X, Y, and Z directions, is just nothing but can be translated into UVW values, but this is a function of two parameters, the H0, the hour angle for the center of the field, and delta naught. As hour angle changes with local time, so then this due to Earth rotation, the same set of the same baseline vector will give rise to number of irretrievable coordinates just because of the rotation of the Earth. Now, so this basically comes to the fact that this is a spectrum. So we observe the sky at a large range of spectrum frequency ranges. This is a particular spectrum given for the VLA or the very large array, and you can see the spectrum supposed to be very smooth because any sky signal should have been much smoother, but in this particular case, it is not a bit smooth, but you can see a lot of this strong features over here, and then over here we have. So what happens is that as you observe at different frequencies, there are man-made transmissions which occurs at different frequencies, and these becomes like noise to us. This is also called radio frequency interference. Radio frequency interference, which is kind of what happens because of the man-made interferences due to the undesired transmission, like cellular phones, aircrafts, satellite communications, military radars, etc. And there are different things. Like here in this particular case, you can see that for the VLA between 1050 megahertz and 1150 megahertz, you can see a lot of these aeronautical signals coming up. And the GLONASS signal is the GPS navigation satellite at 1250 near about. There are different others like air traffic controller, weather balloons, satellite, another GPS GLONASS transmission near about 1550 megahertz to 1650 megahertz, etc. All this will be finally the cell phone tower at 1950 megahertz above. This is all a kind of clouds for entire spectrum. So these are noise, and actually, because of the radio signal is very weak, what is getting observed by the radio telescope, all these signals has to be actually flagged. So you must have seen when we have given this small demo about how the data analysis is done, that there are ways to remove these things, and they're called flagging. Okay, so flagging means you essentially flag or remove the unwanted signal from the data. The data which is not the signal, the data which is not coming from the celestial source, but actually being created somewhere nearby or man-made. Okay. So one thing is that imaging of the data. So we have done the imaging. We said that we have removed the FFP, sorry, the PSF, the point spread function. Now the same expression which we wrote in terms of the 2D Fourier transform. If you remember, there is this AI, where A and I are both functions of L and M. And you have e to the power 2 pi I UL plus dm, dl dm. And that gives you rise to the visibility UV. Okay. Now that is a integral equation, and it's a Fourier transform. Now you can write the same thing in terms of matrix format using something called the Jones matrix formalism. It's a bit sophisticated, so we're not going in details about it. But effectively, you can write in terms of the matrix equation and you can write the A times IM is equal to B observed. And the matrix, the formalism of the matrix kind of takes care of the all the different terms. So anyway, this is how the things are implemented actually in one of the softwares we use for the data analysis for imaging. And you have different steps like you have a data column, the model column, and the final residual. So this deconvolution part has to be done iteratively, and it's a non-linear process. So you basically go through a process of the clean deconvolution as you improve the image of quality of the image. Effectively, what you do is you have a PSF, the one that is convolved with the actual image of the sky, which gives a dirty image. And that is because of the UV coverage, the PSF is created. So PSF UV coverage is a Fourier transform of the PSF. That's how you do. So the go from the actual sky to the dirty image is a convolution. So going back from a dirty image to the actual image of the sky is called deconvolution, which we've done. So the different several arrays in the world which are operating right now. We have spoken about GMRT. We haven't quite spoken about the SKA. So SKA, or the square kilometer array, as you understand. So we spoke about that each dish is the area of each dish is given by something like proportional to pi d squared divided by 4, right? Where d is the dimension, the diameter of the dish. So if you have n number of antennas in this particular array, then you have to simply multiply this by NA, NA number of antennas. This gives you the total area of the total collecting area for the particular array. Okay, and I put in a proportional sign because there's some efficiency parameters involved in this particular calculation. So the whole concept of the square kilometer array is this quantity over here is almost like 1 square kilometer. Okay, that much of collecting area will be covered by this large, gigantic telescope. So the first phase of this particular telescope has started to be constructed. The one which is the lowest, the low band part, going from 50 megahertz to 350 megahertz. That particular telescope will be built in somewhere in Western Australia, and the part which is the mid telescope, 350 megahertz, something around 14 gigahertz. These things numbers are quite a little bit not fixed, so they may vary as the telescope needs to. As the telescope comes to the final design, these numbers may vary. So the more or less design parameter is that there will be the maximum baseline. It will be around 65 kilometers for this particular telescope in the low, and 150 kilometer for the mid. So you can clearly understand. So now you're becoming an expert in this particular thing. So if you're being asked, okay, what is the resolution for SK1 low? You can find out for the lowest frequency, 50 megahertz ish. You can calculate what 50 megahertz corresponds to which lambda, which wavelength. You can put in the value of the lambda, and then you can find what the B max is 65 kilometers, right? So lambda is corresponding to how much? Is about what is the lambda corresponding to 50 megahertz? You calculate that, and then the B max is given by around 65 kilometers. So that's what your number is. So lambda over B max will be your effectively your resolution. So given all these numbers, now you are able to figure out what will be the different resolution aspect for this particular telescope or any telescope given these values. Similarly, you can figure out what is 350 megahertz corresponding to 300 megahertz is roughly 1 meter. So we can talk about 600 megahertz. So let us we can try to answer this. So roughly around let's take a simpler example. So say around 74.5 megahertz, lambda is equal to 4 meters. Okay, and the Bmax is 65 kilometers. So you can easily calculate what will be the lambda by Bmax. Similarly for here, lambda is about 1 meter for 300, so about 600, it is roughly around 0.5 meters. And Bmax will be around 150 kilometers. So you can again calculate the lambda over Bmax. So you can calculate the resolution for this at 600 megahertz. Okay, this is for mu equal to 600 megahertz, and this is for mu equal to 75 megahertz. Okay, so that's kind of where we can move. The another amazing part of this telescope is that the amount of data it can collect through the over time. So the expected data rate is kind of 157 terabytes of data per second, because there's so many elements, so many electronics involved. The data rate is pretty high, and in this particular case, it's 2 terabytes per second. But still, it's pretty daunting. So this is the state of the art current radio astronomy, which is a telescope going to be built, and this is kind of do all the greatest science possible in this particular frequency bands, and we can touch base on them as well. Please tune in for the lectures. We will have this in one of the lectures covered in a lecture video last week. So, but the striking part is that even somebody likes to do data science kind of approach with this kind of telescope is a perfect place to do that. And that's because, see, the amount of data collected in here, 157 terabytes per second, 2 terabytes per second. So this will amount to a huge amount of data rate, and you could apply all different kinds of data science techniques in order to get reliable science out of it, and make sense of what it is doing. This is an artist's conception. This is still stuff under designing and redesigning. This is something how the SK1 mid will look once it is built. This is of the designs are all individual antennas, if you can see, and they have the dish and the feed. If you have seen, it's like an offset Gregorian feed. It's not in the center in the focus. It's in a little bit offset, but it makes sure that all the rays which is coming over here kind of meets in that particular focus, which is near there. Okay. The one with the low is a different kind of design, and these are individual dipoles, each of one of them, and all the individual dipoles kind of make collection of them, and this becomes one tile. It is called a tile. Okay, so individual dipoles are all of these individual dipoles kind of phases up and becomes a single tile, and this is how the SK one low will look like when it comes more or less in this vacuum. Okay, As you might be aware of, there are several different mega science projects in India, and SKA is one of the mega science projects right over here where we are looking into. And this is what we excited about. This is one of the mega science projects which India is part of. The others being the very famous one is right here, the LIGO India, the Gravitational Waves Observatory, then 30-meter plus telescope for the optical observations, and also the Large Hadronic Collider, the Higgs boson experiment. This is quite a more details about the particle physics. Oh, now here is something which we really are doing science. As you know, as you've seen that for actually when we do synchrotron radiation or dense Talon radiation, we are studying stuff which is happening all over the sky. We also can use this kind of large telescopes to stare into the very early part of the universe, looking at much fainter signals. Okay, so here what we are looking is this is the Big Bang over here. Then this is the first last surface of last scattering, or what we can see if we look back in time. We will see only up to here, and we cannot go beyond because of the optical depth. So this is from where we see the cosmic microwave background radiation, or CMBR. What happens after that was the universe expanded and became neutral, and it stayed neutral as because there's no particular source to produce photons to ionize the medium again. So so we waited for a long time, and then finally, after quite 500 million years since the Big Bang, then first stars, first galaxies, first black holes, etc., started forming, and then they started evolving to our current generation, our current day known galaxies, stars, and black holes, etc. So this epoch where the first stars, galaxies, and black holes were formed, the universe also became from the completely neutral to ionized. And this area is called epoch of reionization. And so these are the ages where this extended period, which is not very well studied because of the absence of the suitable probe to do that. Now, with the advent of better telescopes, bigger telescopes, looking with precision, these things become possible. And the particular the probe, which is mostly important, is the hydrogen atom has in its ground state, it has an electron and a proton, and the electron has when it does a spin flip, then it kind of emits a photon at the wavelength of 21 centimeter. Let me change the color. So the lambda of that particular transition is a lambda equal 21 centimeter. The frequency is given as 1.421 gigahertz. Okay, so that's the frequency, and that is the particular transition which we use to probe this particular age. So that's the science part of it. And why wasn't it done before? People tried to do that. This is more precise. So this is the hyperfine transition of neutral hydrogen from 1s half to 0s half. Don't worry about all of these things if you don't understand. This transmission, this particular transition happens with a rest wavelength of 21 centimeter. And it's a very, very powerful line. This particular line is used to study nearby galaxies. Because our own galaxy has been mapped completely in H1. And please look into the videos just for completeness. There will be more discussion on this. The videos will be circulated for this week and next week. Please look into that. But it is just for your own complete information. Don't worry too much about this particular materials for your final exam. So, yeah, there's a particular transition which is a very important probe from nearby galaxies, nearby interstellar medium, which is very important probe. And the same probe is now used to study the early universe. Okay, universe just very nascent from outer Big Bang. So a few numbers just to give you a hint of cosmology. So in cosmology, what happens is we define the distance in terms of something called redshift. Okay, which is the z. So a wavelength, which is the normal transition is 21 centimeter, for a particular z, that transition will be at a larger wavelength, okay, or at a smaller frequency. So what we said the original frequency was 1420.404 kind of megahertz, 405 megahertz, sorry. Okay. So if that particular line is coming from a redshift of say 6 or 7, then this particular frequency 1420 will be divided by z plus 1. Okay, and the lambda will be multiplied by z plus 1 to get the right lambda. Okay, so that's the redshifted thing. And also there is a look back H calculation, which is given over here. Don't worry too much if you are really not missing that. So we'll skip all this and we'll go to area. Next one, yeah, right. So that's a particular transmission, a transition line, right? So we use spectroscopy to kind of look at the lines and understand particular, get an idea about the environment from where it is coming on. Okay, to understand it is a very hot or a cold area, or its density of the particular medium can also be mentioned by that. Those are spectral line stuff. Okay. Now, there's another kind of science we can do with the continuum science, which is discussed. We have discussed at length is something called synchrotron radiation, right? So for synchrotron radiation, what happens is that there's a very it's spectrally very smooth. That means it's has almost no shape in terms of the spectral. It's not like the one with the spectral lines. So here in this case, in spectral line, like in a very small area, you can have like a multiple spectrum like this over like 4 megahertz or 6 megahertz or so like that. But for a synchrotron radiation, like over a large amount of things of hundreds of megahertz, it will have a very smooth kind of a slope. Okay. So there's a difference between the continuum emission and spectral line emission. Spectral line emissions have very fast varying variation in the flux density as a function of frequency, whereas continuum does it very smoothly, very slowly over the frequency range. So synchrotron radiation, this is what we are observing our own galaxy. This particular pattern is for our own galaxy, and we are seeing it in terms of synchrotron radiation at a frequency of 408 megahertz. Okay, a lot of science has been done and can be done using simply the synchrotron radiation at different frequencies. For example, if you have a particular source and you have its spectrum covered at different frequencies, then you can particularly suppose you have a spectrum over here and flux density over here, then you can actually connect them and derive what is called the spectral index. When you do spectral index, you can talk about the electron distribution powering that particular emission. Okay. We can make the same map at different frequency. This is like a very study from 10 megahertz range up to 5 terahertz. That's quite a huge range where you're studying at the galaxy. Okay, let's see. Let's skip that. So if you are looking at again a wide field of view, you also have the chance to detect various kind of things, like you can encounter like this kind of radio galaxies. There are different kinds of radio galaxies. This is a particular image taken at around 300 to 500 megahertz with GMRT. With a huge GMRT. So this is the upgraded GMRT. And we're looking at a particular part of the sky, which corresponds to something called LISN1 or NOC1 field. And so we have made this image in this particular frequency band. And then you can identify individual sources. There are very point-like sources like this one. There are very extended sources like this one or even this one. Okay. And if you zoom into few of them, you can understand the nature of those particular things. Let's look at another image. For example, if you're looking at something like this is another part of the sky. This particular part of the sky is called Lochman hole. Okay, and this particular image is made around at 327 megahertz with the GMRT. And now, if you look at this part of the sky, you see, if you zoom them up, you look at this is called a giant radio galaxy. Okay, you can see the hot spots over here. Similarly, there is also another giant radio galaxy. This is coming from somewhere. Yeah, it's difficult to identify. It's 60 by 60 field of view. Huge image. This is something which is not coming from a single pointing, but we have observed multiple pointings across the sky, and we have what we call it, stitch them together, which is called a mosaic. So you do something called a mosaic, and you stitch all of them together, and you get larger field of view. Okay, it's another one of the techniques which can be used. Okay, so that's a part of the thing. So now another thing is that we have, of course, we do have our cosmic microwave background is there. We have, after that, there is our different layers of dark ages, epoch of ionization. Then finally we have the extragalactic foregrounds, the galaxies, all the stars, then our own galaxy itself. However, all of this signal essentially comes in through they do come in through our own ionosphere, the Earth's ionosphere. Okay, and that gets corrupted when it passes through that particular medium. The ionosphere is nothing but a plasma screen. Okay, so it has electrons, and that makes you know different affects the incoming electromagnetic signals in different ways. We can have so Earth's atmosphere can be also broken up into exosphere, thermosphere, and ionosphere has different layers: the F layer, the E layer, and the B layer. Different layers contribute differently. So if you can see this, there is diffraction. So it acts like a lens. There can be absorption and emission from the D layer. So mostly the reflection happens in F and E layers, and D layer is mostly responsible for absorption. Okay, the density of it is much more. So anyway, this is a plasma screen. It has a lot of effect on the incoming or trans-ionospheric signals. So any signal which is coming from the cosmic sources has to pass through the ionosphere. And as the frequency of the observations or the actual emission of this particular sources coming close to something called the plasma frequency, okay, then this particular effect of the ionosphere becomes more and more stronger. So yeah, you should know how to calculate the plasma frequency. Okay, plasma frequency is nothing but essentially a cutoff. So any rays which has a frequency less than the plasma frequency will basically simply cannot enter the Earth. It will get reflected back from the from the top. Similarly, any kind of signals coming originating from the Earth will never leave the ionosphere. It will get reflected back completely to the Earth. Okay, so that's the effect of the plasma frequency, plasma cutoff frequency. Okay, and it is kind of check one of the lectures last week, week number 12, which will be coming, and we will have the formulation of that. But anyway, this is kind of a function of the electron density of the particular medium, and it corresponds to that. So plasma frequency is not also constant across the entire globe. Depending on the geomagnetic location, the plasma frequency can change. It can also change with solar activities. So just to see why this ionospheric thing is a big problem. So this is a low-power observation of one particular field, which is not important for this particular discussion. What is important is that in the left-hand side, what you are seeing over here is that you're seeing something which is due to a quiet ionosphere. So what you see is lots of waves passing through, but it is not disturbing the major sources. They are more or less steady, right? So let me just get away. So if you see that, if you look at particularly concentrate on this source and this source, you will see they are not leaving this particular area, not that much. Okay, so they're not reflected much in this thing. What's happening is as we move through the frame, there's 30 seconds interval between each frame. Okay, so as you move through, you're probably moving through like few minutes or tens of minutes. And these two sources are not essentially crossing the neighborhood. Now look, switch back to your knowledge, your attention to the right-hand part of the image, and you can see that if I make a hole, it's almost touching the boundaries each and every time. But if I make a closed hole like this, you can see it when it comes out of that, tries to come out of the area, and also succeeds to do that very often. So similar kind of things. This is a much more disturbed ionosphere. And this is a very quiet ionosphere. Now, what happens is when we make an image, we essentially what we do. Remember, we integrate over the visibility with time. Okay, so we keep on adding the snapshots one after the other, bang, 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 and we make a constant image. So this point source, which was looking like this, if I make an image, it will look like wherever it has gone, right? It will look like an extended source, which is supposedly a point source. Now will no longer look like a point source, but it looks like an extended source. That's distortion ionosphere typically creates. Okay, and that's why we are very worried, and we want to take care of the ionospheric effects as things as we try to make better and better images and better and better detections with variant parameters. So yeah, I think thanks for listening. This is the part I wanted to cover and discuss with all of you, and there are lots of more to say. I mean, this is a very short time to discuss a lot of things. I hope this discussions have been helpful, and looking forward to your questions. So please unmute yourself and ask any questions you might have.
Sir, in India, for JMRT and Gauri Bidanand radio telescopes, which frequencies are the most contaminated?
Which frequencies are most contaminated?
By humans, that is radio frequency interference.
There are, yeah, so GMRT has different bands. Okay, there is one band which goes from, let me pull it up. Anyway, I think we can post it, or we can see it in the GMRT website. So one of the band is essentially which goes from the lowest band is about 120 megahertz to 250 to 240 kind of close. That's called band 2. Then there is another one called band 3, which goes from something around 300 to 500 megahertz, roughly, give or take. Then another one from about 550 to 900, and then 900 and above to 1.6 gigahertz. So if you are talking about lower frequencies, like for example, near about 100 megahertz, if you're observing, then the most prominent emission is coming from radio. RFI is coming from something called the FM band. Have you ever watched something called Radio Mirchi or all these things? It's a very, very interesting, very exciting things. But I mean, they themselves are kind of brings bad news to things like our observations. Okay, so the FM band goes from 87.5 megahertz, something like that, to 110 megahertz, and this is really detrimental for things. Even I showed you the examples of the Zipa copper ionization, and our signals, there is a very strong signal around 70 megahertz or so, and sorry, around 90 to 110 megahertz, and we have this band, it's the middle of the FM band. People have tried to observe in places very remote, like Western Australia, and they have been seen, they have been able to see the reflection of this RFI, the FM band, reflected from the moon. So the FM band emission goes and reflects from the moon and comes into your in telescope. Okay, so there's no way to avoid this kind of things. Okay, If you come to higher and higher frequencies, there are different um, satellite downlinks. There is this GSM stations, and if you're using a 4G or 5G, there's a different set of transmission frequencies, and they also become very bad RFI source. But one of the major problem with GMRT was is this high tension wire, right? We have seen this high tension wires of power lines going over like across the country, right? And those when they near the junctions, if there is any slight mismatch or loosening in the couplers, there will be sparks, right? So sparks are like pulses. A pulse is like a delta function in time. Now, what is the corresponding frequency response for delta function in time?
A straight line.
Right, it's a constant.
Yeah,
it's a constant signal. Yeah, so it's constant across the entire frequency range, right? Right.
Yes, sir.
So a delta, impulse in time. So it's a broadband alpha, and those are very dramatically killers of the signals. Okay, so those are very important things, which are one of the very for the particular GMRT side, it was very important, and people did very innovative techniques to get rid of most of them constantly. So yeah, these are some of the very important things. Now there's a huge amount of effort. The International Astronomical Union, along with few other like SK organization, etc., are really behind understanding what will this huge number of Starlink satellites and similar things will do radio astronomy. So this is still something in progress, and you will understand how to coexist, because certain things also are important. You cannot simply stop them from happening, but you have to somehow coexist in bands in certain times. The only problem is if they're limited and they're not crossing their the design things, so we can simply know which frequencies to avoid to the level of kilohertz resolution, and we can remove them. That would have been ideal case. However, nothing is perfect, so things leaks beyond what is the allocated things, and that's how the trouble starts building up. Yeah.
So building radio telescopes on the dark side of the moon might help. Because
that's a dream.
Yeah, because I've read that is the only region where it's free from human-made interference. So there are ideas to build there.
Yeah, so basically there are studies which has and particularly this is very close to what I do. There are studies which essentially say that the far side is quite compatible, and but if you choose the place correctly, there will be quite useful locations where all the RFI can be shielded off. Okay, but as you go to lower and lower frequencies, the moon as a disk shields, but it also there is the effect of diffraction. The things curves around the disk as a wavelength become larger and larger. So some of those part of this free space gets occupied, but and depending on which side, which is the latitude where you want to land, the far side is still one of the best places known in the neighborhood where you can actually build up a telescope free from the RFI and ionosphere. But it's difficult game. People are at it, and we'll see how it goes.
Sir, but I have one question. In cities like Chennai, Indore, Mumbai, etc., Is it possible to make very high frequency observations like around 150 gigahertz? That is somewhat similar to CMB observations.
Good questions. Because I think as we see the ionosphere becomes a problem at the lower frequency, and the troposphere, the water vapor level becomes a problem at the higher frequency level. So till about 20 gigahertz or so, these things are not that pronounced a problem. But if you go still keep going above, particularly above 100 gigahertz, cloud cover is significantly a problem. So you cannot be near the you have to be a little bit higher altitude. So the best places are probably hills, mountains. One of the best known sites in India is Ladakh, Leh, and Leh. There is an observatory by Ministry of Astrophysics, and there is probably one of the best places to make high frequency telescope, not on the coast at the sea level. Not at
Okay,
this
sir.
frequency, which you're telling about, yeah.
Yeah, I thought we can make CMB observations from cities.
It's yeah, I mean, depending on what exactly you want to do. I mean, the quite high frequency observations are not. I mean, it depends on the number of days you will get a clear sky. Okay, the water vapor level, like particularly from say Calcutta, I mean, this is very immense cloudy and all this thing. So, yeah, it's preferred to have a little bit above the cloud cover to make to get more number of days of observing. You can observe, you can do even optical astronomy from the cities, why not? But I mean, depending on the nature of the science you want to do, how precise you want to do.
Like detecting B modes, is it possible?
I haven't seen any any calculation which says that it is possible from this thing, but yeah, I think you need a better site to get this kind of thing done.
Okay, sir.
Okay, if nothing, then thanks for joining, and stay tuned for the last assignment. And I think they're pretty much very simple, and they're not too new. It's basically revision, more or less, and what we will produce is a couple of more lectures, videos, mostly completing the topic of applications, where all these things will fit in, talking about pulsars, spectral line, continuum observations, nature of continuum observations. But I mean, if you're particularly worried about, again, particularly worried about the final exam, I think take a look at the assignments, and we will also post some more materials if needed. Okay, so see you next week on Wednesday, and before that, everything will be posted, and so stay tuned and come back, go through all the materials. If you see there is anything remaining, just bring that list, because we will collect those feedbacks next week on Wednesday, and we will try to address them as soon as possible within that particular week. And as we're coming to the end of this. Okay, you have my email ID, etc. And so you can please feel free to contact me if you have any questions or comments. Also use the NPTEL platform, do the same. Thanks a lot. Good night. Bye.
Excuse me, sir.
Yeah, right.
Sir, we received the week 10 assignment this week. So aren't we supposed to get 2 more assignments?
No, I think week 11 is coming up.
Sir, week 11 will come on Monday, I think, sir.
No, this is actually week 11, but till now we have got only till week 10.
Harsha, are you there?
Yes, sir. Assignment has been shared with them. They might. I will inquire when will they post the assignment. I think after the week 11 ends, they will post the assignment in around Friday or something.
Okay, maybe. Yeah, we have given week 11. We are just to keep the week 12. But yeah, don't worry. I mean, there won't be any if any issues. Just we will inquire and come back with the question.
So
Sir,
also,
disconnected. Can you please repeat what you said, sir?
From our side, we have given the week 11 already. They might be following a structure. Okay, and so stay tuned for that. If you have any, I will also ask about this and get back to you by next week. But don't worry about anything. Just keep doing whatever has been asked because it won't be penalized for anything.
Okay,
sir,
sir.
also can you share examples or samples, full length question papers of the example? Because it will be useful for time management.
Yes, I understand, but it is. I think we have checked that QP will not be too long. It's I think we have suggested for 3 hours of full exam. And I think it just please follow the structure of this thing. And this is just MCQ and anything questions, and we will try to see if we can give one more this thing. But I mean, it's very unlikely that we can come up with another set which is just can be termed as just a practice set because there are a lot of questions and I think we have roughly around 30 MCQs and roughly around 13 1-3 energy type questions over there. If I'm not mistaken, yeah, I think so. Yeah, so I think please keep an eye on the assignments as we keep on saying constantly. Also keep an eye on the example, solved example lectures if you're too worried about the final exam.
No, I'm asking like how many questions, total number of questions that will be asked for 3 hours. I'm asking for time management purposes.
There are 30 MCQ type questions and 1-3. I think that is true for around 13 to 15. You can say give a range. Numerical assignment, numerical answer type questions. There's no descriptive questions, nothing of that sort. Okay, it's all online exam. Okay, so you should be able to use a standard calculator given by PCS to answer all of those questions. Yeah.
So around 45 questions, sir, total.
Yeah, but they're of varying, complexity, or you can say varying amount of calculations needs to be done. Not all of them have a similar grade of complexity. So we have gone through it. I think you should be able to complete it well within given time, maybe quite before. Yeah.
So will there be negative marking for wrong answers?
This is a good question. I will get back to you after I talk to the team. Thanks. But we will definitely get back to you. Please
Okay.
ask me again.
Negative.
Ask me again. Yeah, Harsha, do you know about it?
No negative marking.
Okay, sir. Thank you, sir.
Just relax.
Sir,
Just
can we get
enjoy.
2 assignments for week 12, sir?
Sorry?
Sir, can we get an extra assignment for week 12 so that we
they,
can boost some
the
scores?
team does not allow to do that. Okay. Even if we give 2, they will be just filled as 1.
Okay,
So
sir.
I mean, we can increase the number of questions of number 12, but they can normalize evaluation out of 100. I think something like that, as Harsha I think clarified. Correct?
Yes, sir.
Don't worry. I mean, I'm again suggesting please don't worry. Yes, I do enjoy what you are learning. I think it's all. But yeah, please go through all the lecture notes. Please come back with any lacuna you find by next week for sure, and we will definitely address them and put it up immediately. Okay.
Sir, one last thing, sir. Is there some way to use CASA on Windows, sir?
There is a Linux for Windows, and
Okay, sir.
you can utilize that. But Casa has to be run from Linux. But nowadays you can also use AWS cloud computing. Okay, so you can,
Okay, sir. Thank you, sir.
install it. Very good question. If you really want to know more, just drop a mail. Okay.
Yes, sir.
Great. Okay. Thanks for joining. Bye bye.
Thank you, sir.
Thank you, sir.